Hello everyone and welcome to today's video. We are going through 6 of the latest questions from the topic of principles of flights, and today will be slightly different as I'll try to show you some extra infographics. However, all of these, the ones that you'll see, are also available on our Instagram, so this just shows you how useful they sometimes can be. So if you don't, then I highly encourage you to follow us on Instagram at Airhead in order for you to get these infographics every other day so you can keep your knowledge sharp. In any case, without any further ado, let's jump into question number 1 from Principles of Flight. So what information can be obtained from a maneuvering load diagram? So this is a very popular question, and there's a little trick because the maneuvering load diagram can often be confused by the gust load diagram. However, the maneuvering load diagram essentially gives you your load factor, your speeds, and where the aircraft stalls. So you can basically associate each speed with its stalling load factor. This is very useful in order to get your maneuvering envelope, for example. So of course, from the answers that you can see right here, it will give you your maximum load factor at stall. For these questions, before I show you the diagram, because I think it's best to visualize it, I just wanted to remind you quickly the difference between a limit load and the ultimate limit load and the safety factor. The limit load is usually the load that is expected during service. Your ultimate load is the load where the aircraft structure will fail, and the safety factor will be the ratio between the two. So this is just a quick reminder for the exams. To what I was referring earlier, these are the two diagrams. So VN diagram, also called the maneuvering envelope, and on the right side you can see the gust load factor graph overlapped over the VN or the maneuvering load diagram. So you can see on the left side where we have the VA, our maneuvering speed, you can see for the speeds where the aircraft will stall at each load factor. And on the right side, if you look at the gust load factor, this is the one where you have the different gusts in feet per second. You can also see the design speed. So these are very important for the exams as well. So this is a great reminder. The maneuvering speed is the speed above which you cannot make full deflections of the control surfaces as you risk destroying the aircraft. Simply put, of course, the VB, max gust intensity speed. Then we have the VC, design cruising speed. And lastly, the VD, design dive speed. And remember that the VNE, so the never exceed speed, will usually be at 0.9 of the VD. So these are just a few information squeezed in a short time for this topic. Now let's go into question number 2. So while a multi-engine airplane is taking off on a wet runway, the airplane starts becoming uncontrollable with significant yaw. This is due to... This question is extremely simple. It may sound a little bit confusing, however, of course, when you are taking off with the airplane and it starts yawing uncontrollably, the first thing you think about is engine failure. So of course this will be due to the asymmetric thrust. If one engine fails and the other doesn't, then of course the aircraft starts yawing. The other ones, so the slipstream effect and gyroscopic effect, these are turning tendencies linked specifically to a single engine aircraft, and this is why we need to apply right rudder on takeoff and what happens as we change different angles of attack. However, this is a topic for a different discussion. And lastly, the CG being close to the forward limit. Actually, this forward limit CG, what it does, and we'll talk about it in the later question, it increases the stability of your aircraft. So actually, this will help you maintain the center line even in case of your engine failure. Here, just a quick reminder about the critical engine. So remember that due to the P factor, the thrust is slightly offset from the center of the aircraft. So if we have clockwise turning propellers, then the thrust vector is slightly to the right side, meaning if the left engine fails, we have more yawing moment as if the right engine fails, meaning the left engine is the critical engine. And for the questions, also remember that if there is crosswind, then the engine that is upwind will most likely also it could be considered the critical engine because it will increase the yawing moments. And now for question number 3. So upon extension of a wing spoiler, if the angle of attack remains constant, what will happen? And this question is slightly confusing. However, I'll try to give you some tips on how to understand this. So the correct answer here will be your coefficient of drag increases and your coefficient of lift decreases. Now, it's easy to confuse here the lift and coefficient of lift. However, of course, the coefficient of drag will increase because we increase the surface area and others. So of course the drag is as a whole will increase. However, what happens to the coefficient of lift? And this is a great opportunity for us to take a look at the lift equation or the lift formula. So of course, besides others like the surface speed and the density, we have the CL, the coefficient of lift, and the CL hides three key things that you need to remember for the exams. So it will be the angle of attack, the wing shape, and the thickness of the airfoil. Generally speaking, the coefficient of lift basically tells us how effective the airfoil is at producing lift. If we change the shape of the airfoil, which spoilers effectively do, we will change, we will change the wing shape. We will change the wing shape of the airfoil. So the CL will decrease dramatically in this situation. And of course, our lift as a whole will also decrease as a consequence. And now going into question number 4. So this is a question that I was already referring to. And although it may seem easy, it's great to revise these principles as this will be helpful for flight planning, for mass imbalance, performance, and the principles of flights, of course. So these are the effects of forward and aft CG positions. And generally speaking, a forward CG is something that we like because it increases the stability. However, it decreases the maneuverability. However, when we're flying fast and with airliners, we value comfort of the passengers. So we want the stability to be there as this increases safety, as well as we're not maneuvering much. So this is an absolutely good balance. However, it also has some implications when it comes to the performance of the aircraft. Because with forward CG, your tailplane needs to create some downforce, and this downforce acts in the same direction as the weight. So now we have an increased value of weight, so we need to create more lift. And this will decrease our range, increase fuel consumption, and also it will increase our stall speeds, which is an adverse condition. This is not something we want. When it comes to the other questions, of course, the V2 is something different. This will be our speed at screen height during takeoff, and usually the V2 becomes our target during an engine failure. When it comes to VMCA, so minimum control speed in the air, the forward CG, because it increases our stability, it will actually have positive effects on the VMCA. So it will reduce it rather than increase it because, again, we have increased stability. However, some aircraft do not want the forward CG. So, for example, the aerobatic aircraft or military aircraft, and these will have CG more aft because they want to be more maneuverable, and stability is not something that desirable there because, of course, they will do crazy aerobatics and crazy maneuvers. And there are some other effects of the forward CG. So, for example, the decreased max speeds, of course, reduced range, as we already discussed, more fuel flow, which translates into the range, and increased stall speeds. So, as you can see, here on the diagram, the tailplane creates a downforce in order to offset the forward CG, which acts into the same direction as our weight. So we need to produce, simply put, more lift. And now going into question number 5. So when a strong swept back wing stalls and the wake of the wing contacts the horizontal tail, the effect on the stall behavior can be what? And this is very, very important, and this is a question that can be asked during your airline interviews as well. So the characteristics of a swept wing and the stall characteristics of that wing. And this is very different than a straight wing. So once you change from flying the general aviation aircraft like the Cessna or Diamonds, which are usually straight wings, into swept wings, this can be very surprising because a straight wing will have heavy buffet, and at the stall, usually the nose will drop down. This is because, of course, the center of gravity is usually more forward than aft, and the aircraft will recover more or less on its own with a heavy buffet felt on the controls. Here, it can be very, very different. Because the swept wing goes to the back and stalls at the tips first, this means that the center of pressure as the aircraft is stalling is slowly moving forward towards the nose. And this forward movement of the center of lift or the center of pressure will actually create a nose-up tendency, and the wake of the high lift creation and the roots of the wing If it touches the elevators, it can deem them almost completely ineffective, meaning we can go into a deep stall or an unrecoverable stall where we lose all authority on our elevators, and we simply go down into stall. And also a heavy consideration here is that this stall can often go unnoticed for a long time. And here the main giveaway will be an excessive rate of descent, because sometimes the buffet cannot be there and there is no nose down tendency. And now for the last question, so question number 6. So this is also a relatively straightforward question. However, it's always good to revise different speeds and take a look at an airspeed indicator, which I'll show you in just a second. So a VFE is the maximum speed at which, and of course the correct answer here will be with the speed at which with the flaps can be extended. And so of course we cannot fly, we cannot extend the flaps above the VFE, as we risk destroying the structure. On some of the more advanced aircraft like the Boeing or Airbus or the airliners as a whole, the system will give us actually the VFE, because there are many flap settings from flaps 1, 2, 3 or 4 and 0 on an Airbus aircraft. The VFE next will be displayed so we can know what the next flaps extension speed is. However, on the other aircraft, mainly speaking the training aircraft or the GA aircraft, we have the analog airspeed indicators, and they have many different features, so many different things besides just the VFE. So of course we'll have the VSO going from the first speed, which will be our stall speed in landing configuration, then the VS1, which is stall speed in clean configuration, then we have our white arc, so this is our flaps operating speeds, and the VFE marks our flaps extension speed, so we cannot extend the flaps past the VFE because we risk destroying the aircraft. We have the green arc, which is the normal operating region, VNO, normal operating. Then the yellow arc, these are the speeds which can be flown only in smoother conditions. And lastly, we have the VNE, so never exceed speeds, which is at roughly 0.9 of VD, which is our design dive speed. Here also, when it comes to the multi-engine aircraft, we will have our best of rate of climb speed with single engine VSEY, and this will be marked with a blue line on the airspeed indicator. And this will be everything for today. So thank you again for watching. I hope this is interesting and slightly different today with some infographics. Let me know if this was helpful, and I wish you all the best with your upcoming exams. Have a fantastic day, and I hope to see you in the next video. Bye-bye.